So I just made a video on the daily solution for number of good paths, and I wanted to just quickly explore my kind of quirky code and explain what was going on with it. So this is what I wrote. I'm just going to copy paste this. You can see it's got a lot of random comments and stuff that I was making to myself. And actually I think that's the utility in this video, is looking at the thought process around this. So I was getting ready for the coding competition last night, and I had a beer and I was kind of just like blasting music and seeing how quickly I could do this was the main thing, and kind of getting pumped and stuff. So now I'm going to kind of try and be an archaeologist and piece through. So the first thing I do is I make an adjacency list, and then I do something kind of interesting here, this little optimization. I make this scan function and this lone dictionary where I'm just counting up every single instance of every node's value and then adding one. So now I have a counter with every node's value. So here it would be like 3, there's 2 3s, there's 2 1s, and there's a 2. And then I say lone is now a set that only contains the things where there's only one node. And the reason why I do that is to later on I kind of realize that a stack is kind of a useful data structure for this problem, and I use a depth first search using this like stack recursively, and I realized that like I don't want to gunk up the stack with a bunch of random values if there's only one of that value. I don't want to bother, and it seems like a lot of the test cases only had one value. There was a specific test case where there was like 50,000 edges between node 0 and every other node, where every other node was only a value 1. And I was like, that would go from being a nightmare situation to being like extremely quick if I just kept track of which nodes there was only one, which on average helps, but if you think about it, it doesn't really affect the worst case at all. But it's still an interesting idea. And then I make a disjoint set algorithm, and this is just very straightforward. And I realize a couple of things here, but I'm using this disjoint set in a different way than the previous solution I went over, where the previous solution is just using Kruskal's algorithm pretty much, where you're connecting the edges with the lowest maximum value for each node. But here I'm just connecting with a depth first search, and I'm saying just start at any old random node, who cares? And the idea is you explore out and you find, you add to the stack the current, all of the current paths that are potentially being formed. And you keep track of that. You keep track of exactly in the current little path that you're on, the current little pool that you've formed in this local minimum, which values for which node are permissible in that path, and how many of each value. And then you continue, and then let's say here you run into this 2. I use this like really sloppy leftover list of lists to just say, all right, drop off everything that doesn't work at this 2. So let's say you look at this 3, and then you're looking at this 2, and you have node 0 and node 1 with a value of 1 and a value of 3. You say, well, drop off node 1, that doesn't work anymore. And now you have nodes 3 and you have this value 3 and this value 2, and then continue. So here you don't have to drop off anything. And then here you have to drop off node 2, but then you have node 3 at the top. And you know, if you form this as a stacked structure and you keep it ordered like that, where anytime there's anything lower than a node you're passing through, you drop it off at that node until you reach something that's at or higher than it. That means that, let's say this was 2, you'd always have a 2 at the top if you had a 2 in your stack. So let's say here you would have this 1 at the top if it was possible. So because you drop off the 1 and then here you're looking at node 2 and 3, you know that there's no path that can be drawn from anything up above. But here you drop off node 2, you drop off this value 2 when you reach this node with value 3, and then you have 2 nodes of value 3. So I say, okay, traverse through and while all the nodes at the top of the stack are lower, drop them off. So create this list L and just append all the popped values to that, and then run a depth first search there. And then once you're done, let's say you went here and you ran a whole depth first search down here. Once you're done and you come back to this, let's say there was like a node with a value 4 and you drop a bunch of stuff up there. Once you come back through, pick that back up and put it on the stack, and then continue. So that's stack.extend. And also once you come back, get rid of everything below. Don't even drop it off, just get rid of it that can't come back through this node that you picked up down below. So let's say this node had value 4, and then there's a bunch of 1s and 2s down here that you're rooting around in. Once you move back up the recursion path and you've solved this subtree, now everything that's lower than 4, maybe there's a 5 or a 6 down here you can use, but if there's a bunch of 1s and 2s, they can't come back up through the 4, just like the 1s and 2s up here couldn't go down through the 4. Yeah, so do that, and then let's say there's a bunch of 1s and 2s up here, connect them using a disjoint set. And only connect nodes, for example, this node 1 and node 4, if the values are the same. And then what we can do, let's say there's a bunch of 3s up here, there's like 10 3s. The other algorithm kind of calculated 3 choose 2 in a different way, but here if there was 10 connected 3s, then the size of this set would be size 10. And then in the end, we just say, well, there's 10 3s here, so what would that be? 45. There's 45 different connections you can make between 10 nodes, between any 2 of those 10. And then in the end, just return that. So it's confusing. I really liked the use of the stack. It had like it's like a monotonic stack use, and those are already very mind-bending to use on a normal one-dimensional array. So using that in a graph problem, I'm pretty proud of. And to be honest, this algorithm holds its own. It's I would chalk that up entirely to the test cases. You could get some mean test cases that would make this exceed the time limit, but they didn't quite seem to cover those extremely niche cases. If I mentioned there was a problem where there's one node 0 connected to 50,000 different individual nodes, if that was connected to 25,000 nodes and then each of those had a single node connection, and you changed the values of those to be very exact, that would stop this up. But that's such a weird corner case. Like, I'm almost impressed that I was able to come up with an algorithm. It's almost like a riddle that's technically solvable but basically impossible. Like an algorithm where you could technically stop it up, but I don't know that you could ever come up with that solution without looking at this algorithm and deconstructing it, or come up with that test case that would jam it without looking at this algorithm and deconstructing it. The last thing I'll say is for a minute, I tried to actually make the adjacency list be heaps so that these would be ordered in terms of their lightest edges, which was an interesting idea, but I don't think it really affected the time complexity. So a lot of quirky things going on here, a lot of weird commented out print statements and such. I just was seeing how quickly and sloppily I could do this, and I think it's a testament to 2 things. The first is if you have a vision and you're confident enough in disjoint sets and graph theory and stuff, you can kind of just go for it. And sometimes it won't work, but a lot of the time, if you stick through all the weird corner cases and stuff and you add enough things to account for that, it does just work, and it works fine despite being nowhere near as elegant as the original solution. And the second thing to me is like this idea of perfectionism. I really like this problem because I think it shows up a lot in terms of like personal psychological growth in people, but the idea of perfection I think can be damaging because it's phrasing things in terms of there is one best solution, and anything that deviates from that has a deviation that needs to be mitigated, as opposed to thinking of it more as there are many solutions you could construct, and constructing anything is an accomplishment in its own right. That being said, that's a pretty large rationale for this when this is just inferior to the other solution. And that's the other kind of lesson here, is that even something like this you can get even more knowledgeable about graph theory and disjoint sets to come up with something much more elegant. So that's my solution. I just wanted to share it.